Welcome to the next lecture in Module 6 on finite volume methods. In the previous lecture we had a brief introduction to finite volume method, and we had a look at how do we approximate finite volume integrals. In this lecture we are going to focus on finite volume interpolation schemes, and in the next lecture we will have a look at some applications of finite volume to scalar transport problems. Now, let us have a brief recap of what we covered in the previous lecture. We discussed the beginnings of finite volume method, that is, what is finite volume solution process, what type of finite volume grids are used, and we also had a look at approximation of finite volume integrals, namely the approximation of surface integrals and approximation of volume integrals. Now, in current lecture we would focus on the interpolation schemes which are used in finite volume method. So, brief outline of the lecture. We will have a look at why do we need interpolation schemes in finite volume method, and then few most commonly used interpolation schemes, namely upwind interpolation, linear interpolation and quadratic upwind interpolation. We will also have a very brief look at other recently used or developed interpolation methods. Now, why do we need interpolation in finite volume methods? In the previous lecture we have seen that we need evaluation of surface and volume integrals in our finite volume formulation, but the surface as well as volume integrals, they require the value of the unknown variable at locations other than the computational nodes of the CV. So, somehow we have to come up with some sort of scheme or mathematical approximation to compute the values at these locations, and that is where we need various types of interpolation formulae. Now, the various possibilities for interpolation include upwind interpolation, linear interpolation, quadratic upwind interpolation, and recently developed hybrid schemes, TVD, that is total variation diminishing schemes, and ENO, essentially non-oscillatory interpolation schemes. Let us have a look at each of these schemes one by one in bit more detail. So, first is our upwind interpolation scheme. Where we would require upwind interpolation scheme, it is essentially used for what we call convection dominated problems, and here the velocity at a given point, the direction of that velocity, that determines the variable values to be used in the interpolation process. The name upwind refers to that we are going to make use of the node which is upwind or upstream of the given node. For instance, if we are at the east face of a control volume, now in that case for a function f, we are going to approximate it. F is given by f at p, where p is the point which is to the left of the face E, if v dot n at point E, that is the velocity component at point E in x direction, that is pointing towards the positive x axis, that is when we will get v dot n at E is equal to 0. And in case the velocity is directed in negative x direction, then our upwind node becomes the node capital E. So, in that case f small e is equal to f capital E if v dot n E is less than 0. Now, this use of upwind interpolation, we also call it UDS in short, it is equivalent to using a backward or a forward finite difference approximation depending on the flow direction. And before we look at the advantages and disadvantages of the upwind interpolation scheme, let us have a look at why we say that it is equivalent to a forward or a backward difference approximation. So, let us move on to the board and have a look at the characteristics of this upwind interpolation scheme. So, let us first draw a schematic diagram. So computational node capital P, node ist to it capital E, and we want an approximation for the function f at the eastern face denoted by a small e. Now, upwind interpolation scheme, suppose u velocity is equal to 0. So, by definition what we had in UDS, f at E would be approximated by value of f at point P. Why? Because now in this case our v dot n at E, this is greater than 0. Now, in what way it is related to the first order difference approximations or one sided difference approximations? For that, let us make use of a Taylor series expansion. So, using Taylor series expansion, the function value at any point near our computational node P, this can be approximated as f at P plus x minus x P del f over del x at P plus x minus x P square del 2 f over del x square at P plus so on. So, now what would be the value of function at ist node small e? At the eastern face, f e, this would now be f at P plus x e minus x P del f over del x at P plus x e minus x P square del 2 f over del x square at P plus higher order terms. So, now let us have a look at the UDS approximation which we have shown earlier. Let's number this equation as 1, the Taylor series expansion 2, and Taylor series expansion for the function value as equation 3. Now, if we compare the equation 1 and 2, what do we say? That error in our UDS approximation, so comparison of UDS approximation one with Taylor series expansion clearly shows that we have made an error. That error in UDS approximation is, let's call this error as epsilon. So, this is x e minus x p del f over del x at P plus higher order terms. Now, x e minus x p, that is half of our grid spacing. So, essentially it is proportional to delta x, where delta x is the grid spacing. So, this error is proportional to delta x. So, this epsilon is of order delta x, and that is why we say that, look, the UDS expansion is similar, or UDS interpolation is very similar to our forward or backward difference approximation, both of which have got an order of accuracy as 1. Now, next let us see what other things UDS approximation introduces. Suppose f were a convective flux. So, suppose function f is the convective flux given by, it is f is equal to rho u is the velocity component in x direction, and phi is the scalar quantity whose flux f represents. So, now in this case, what happens to our error? Thus error E, if u is assumed to be constant, this is x e minus x p times rho times u del phi by del x at point p. Now, if you compare it with the definition of diffusive flux, so compare epsilon in 6 with diffusive flux. Normally diffusive flux, let us call it Fd, this we would represent as gamma times del phi by del x. So, if you compare these two expressions, it is our f d to gamma del phi by del x at p, gamma is diffusivity. So, then what do we get? That epsilon essentially represents a sort of numerical flux or numerical diffusion with numerical diffusivity. So, this epsilon represents an artificial diffusion flux with diffusivity gamma numerical. This is given by rho u x e minus x p. So, in essence, use of this upwind interpolation leads to an scheme which is first order accurate. That is what we got from the equation number 4, and in addition this scheme introduces numerical diffusivity or numerical diffusion in our solution process, where a numerical diffusion coefficient can be given by rho u into delta x by 2. So, now let us have a look at the further characteristic of this scheme. What are the advantages of this scheme? Now, upwind interpolation is the only approximation that satisfies boundedness criteria unconditionally. Unconditional in the sense that irrespective of what the velocity values are and irrespective of what is the grid spacing, the solution will always remain bounded. That is, the use of upwind interpolation will never yield oscillatory solutions. This advantage is coupled with the disadvantage which we have already seen. The first one is it is numerically diffusive. If we have got sharp peaks or oscillatory values which are actually present in the solution, those will be damped out because of the presence of numerical diffusion. So, the numerical diffusion is magnified in multidimensional fluids, especially if the flow is oblique to the grid face, and peaks or rapid variations in the variables would be smeared out because of the introduction of additional diffusive coefficient, what we call numerical diffusion coefficient, by the use of upwind interpolation scheme. And we have also already seen that it is only first order accurate. So, hence we require very fine grids to obtain accurate solution. But nevertheless, the advantage which this scheme provides, that is the unconditional stability, specifically for advection dominated problems, UDS is still very popular. We can go for very fine grids, and we can rest assured that we will not get a solution which becomes unbounded. The next interpolation scheme which is also very commonly used is linear interpolation, and in short it is called CDS, that is central difference scheme. We will see very shortly what is the correlation between the central difference scheme which we have learnt earlier in finite difference module and the simple linear interpolation. So, now here we approximate the value of a variable at the cell control volume phase center by linear interpolation of the values at two nearest computational nodes. So, for instance, if you are looking at the east phase, so function value at the east phase, that would be a linear interpolation of the function value at the capital E, that is the eastern node and the current node P, and we use a weighting function lambda E. This lambda E would depend on the relative locations of the computational nodes capital E and capital P with respect to eastern phase. So, F E is equal to f at capital E multiplied by lambda E plus f p 1 minus lambda E, where lambda is given by x E minus x capital P divided by x capital E minus x p. Now, this linear interpolation is equivalent to the use of central difference formula of the first order derivative. Hence, this scheme is also termed as central difference scheme or CDS. So, before looking at the characteristics, let us see mathematically, let us derive what are the characteristics of linear interpolation scheme which make it identical to our central difference approximation. And let us draw a schematic diagram. So, x axis, so computational node capital P, computational node capital E, and these are boundaries, the control volumes. And suppose we are interested in finding out the values at the cell phase small e, and for small e we wrote the formula that f at small e would be given by lambda e times f at capital E plus 1 minus lambda e f at capital P. So, this was our linear interpolation formula, and we had defined lambda e. Just for recapitulation, let us note it down. This was given by x at small e minus x p divided by x capital E minus x capital P. Okay, now to obtain the function value at node E, first let us write down a Taylor series expansion in terms of the function value at our computation node capital P. So, this Taylor series expansion around node P gives us that f at E, this is equal to f at capital P plus x small e minus x capital P del f over del x at P plus x small e minus x capital P whole square divided by 2 del 2 f over del x square at P plus other higher order terms. Let us call this equation as equation 2. Similarly, we can also find out the function value at the eastern computation node f capital E. So, function value at node capital E in terms of Taylor series expansion around node capital P. So, this will give us f of capital E is equal to f of capital P plus x capital E minus x capital P del f over del x at P plus x capital E minus x capital P whole square divided by 2 del 2 f over del x square at P plus higher order terms. So, let us call this equation as equation 3. Now, let us eliminate the first order derivative terms so that we can obtain an expression for f e in terms of the function values using equations 2 and 3. So, now let us multiply equation 2 by x capital E minus x p and equation 3 by x e minus f p and subtract these two. So, x e minus x p times your equation 2 minus x e minus x p times equation 3. This will yield, let us see what do we get, f e minus f p times x capital E minus x p. This is what we have from this second equation, the first term, minus f capital E minus f capital P times x e minus x p. The first order derivative terms will simply vanish and we would be left with the second order derivative terms. So, plus 1 by 2 del 2 f over del x square at P multiplied by x e minus x capital P whole square into x e minus x capital P from equation 2 minus x capital E minus x p square into x small e minus x capital P. So, here we have got this is equal to. Okay, now these terms on the right hand side, they represent an approximation in terms of these differences in mesh spacings. Okay. So, now if we approximate or if we think of it as an error and neglect it. So, neglect of RHS else FE minus FP XE minus XP equal to F capital E minus F capital P XE minus XP. And if we rearrange the terms here, we precisely get our interpolation formula, that is FE is equal to XE minus XP divided by XE minus XP times FE plus one minus XE minus XP divided by X capital E minus X capital P times FP. Okay, so now if you compare the equation 6 with equation 1, these two are identical. And what is error made in approximation? Error is what we have neglected. So, let us call it epsilon tau. This is equal to, rather this is of the order of your X E minus X P whole square. So, thus our linear interpolation is second order accurate, and we call it central difference approximation, simply that if we want to find out what is the derivative of f at our eastern node E, if you work it out, that derivative will be in terms of the values at two nodes on both the sides of small e, that is capital E and capital P. So, the formula for del f by del x at E, that would be essentially equivalent to the use of a central difference approximation, and that is the reason why this linear interpolation scheme is referred to the CDS scheme. Let us get back to our presentation and look at the characteristic of scheme. The CDS scheme is second order accurate. So, from now onwards we will refer linear interpolation by its short acronym, that is CDS. It is second order accurate. The accuracy is very good, but we might have one small problem for advection dominated situations, that this scheme may produce oscillatory solutions. So, that is the negative side. On the positive note, it is simplest and most widely used interpolation. We need to worry about oscillations only when the grid spacing is fairly large. With small grid spacings, we do not have to worry about the oscillations present, and in that case CDS gives us a choice of a very good and very simple second order accurate scheme. So, that is the reason why it is used very commonly, especially in the flow simulations which require the use of fine spatial and temporal grids. For instance, if you are looking at the simulation of turbulent flows using large eddy simulation or direct numerical simulation approach. And not just that, it leads to a very simple approximation for evaluation of gradients, and gradients are the ones which we require in the evaluation of the diffusive fluxes. So, that is why it is very popular. Okay. And this approximation of gradients has second order accuracy on uniform grids. On non-uniform grids, we have already seen in the case of finite difference discussions that it is formally a first order, but nevertheless as we refine the grid we get an accuracy which is close to second order. So, that tells us why the CDS scheme is very popular in CFD community. Our next scheme is what we call quadratic upwind interpolation scheme. We had a look at upwind scheme which was first order accurate, which we said it takes care of the presence of the high velocities or the advective fluxes. We do not have to worry about introducing oscillations in the solution, but the downside is UDS is only first order accurate. Then we will had a look at linear interpolation. Linear interpolation is second order accurate, but it is prone to producing oscillatory solutions. So, the next thing was, can we get a second order accurate scheme which has got better damping properties than CDS and it has got better accuracy than UDS. So, this quick upwind interpolation scheme was devised for this particular purpose. The name upwind which is still here, that tells us that we are going to give more prominence or more weightage to the function values at the nodes which are on the upstream side. Okay, so, now let us have a look at eastern phase. So, approximate the value of the variable at a CV phase center by using quadratic interpolation of the values at 3 nearest computational nodes. And which will be these 3 nearest computational nodes? We are going to use one downstream node, let us denote that by capital D, and 2 upstream nodes capital U and capital UU. In this generalized description, we have not used capital P or E or capital W, which we normally use to denote our computational nodes on eastern or western side, because it depends on the direction of the flow velocity. For instance, if you are looking at a flow in positive x direction at the cell phase E, then our upstream node will become the node capital P and downstream nodes will become capital U is identical with capital E and UU becomes capital EE, that is east to east. So, let us first have a look at this generic formula that FE is F capital U plus G1 times FD minus FU plus G2 times FUU minus FU, where these coefficients G1 and G2 they are based on the mesh spacings XE minus XU, XE minus XUU divided by XD minus XU times X capital D minus XUU, and G2 similarly given as XE minus X capital U times XE minus XD divided by XEU minus XU times XEU minus XD. Now, let us have a brief look at how do we obtain this formula, and for that let us move back to our board. We have already seen one thing, that we are going to use quadratic interpolation scheme, and for that quadratic interpolation we need values at 3 mesh points. Let us first draw our schematic diagram. So, our eastern phase, this is one cell, to the next cell, our computational node capital P, capital E, capital EE, and the western node capital W. Now, let us have a look at the phase center is small e, where we want to obtain approximation of our function variable. Now, if the velocity at E, flow velocity, is in positive x direction, then in that case our downstream node will be the eastern node. So, if u e is greater than 0, so in that case downstream node, that is the eastern computational node, the first upstream node, that will become our computational node capital P, and upstream to upstream, that will become our node capital W. So, u is node capital W. In contrast, if we had the other way around, that is, if the velocity at phase is less than 0, that it points in negative x direction, in that case our downstream node, that will become the node P, and the first upstream node will be the eastern node capital E, and the second upstream node will become E E. So, there are two situations which we might have. So, to keep our discussion generic or general, let us work out the formula, let us use this quadratic interpolation using the symbols d, u and uu. So, we can approximate this function f can be approximated by a quadratic interpolation f at x, this is equal to a0 plus a1 times x minus x u plus a2 times x minus x x u whole squared. So, let us call this equation as 1. Now, here a0, a1 and a2 are the coefficients which we need to work out. Now, what will happen if we choose x is equal to xu? So, at x is equal to xu at f capital U is equal to a0. So, we get a very simple expression for the coefficient a0. Similarly, now let us apply this or use this formula to get the functions values at the node d and uu. Similarly, your fd equal to a0 plus a1 times xd minus xu plus a2 times xd minus xu whole square, or we can rearrange the terms and we can write a linear equation for a1 and a2 as a1 times xd minus xu plus a2 times xd minus xu whole square is equal to fd minus fu, where we have substituted for a0. So this is our first equation in terms of the unknowns a1 and a2. Let's number this as 3. Similarly, for x is equal to x uu, we will get that f at uu is equal to f at capital U plus a1 times xuu minus xu plus a2 times xuu minus xu whole square. Rearrange the terms. So we get a1 times xuu minus xu plus a2 times xuu minus xu whole square. This is equal to fuu minus fu. So let's number this equation as your equation 4. So now we've got two equations 3 and 4 in terms of two unknown coefficients a1 and a2. It's a very simple linear system and you can easily solve. So that I am going to leave as an exercise. For instance, you can use Cramer's rule to solve this system. So using Cramer's rule, your a1 would become the determinant fd minus fu, fuu minus fu, and xd minus xu, xuu minus xu, divided by capital D, where capital D is the second order determinant given by the coefficients in these two equations, that is xd minus xu, xd minus xu whole square. Sorry, here we should have the square terms here. Xuu minus xu and xuu minus xu whole square. Okay. Similarly, we can write an expression for a2, and thereafter you can combine the terms together. Similarly, you can determine coefficient a2 using Cramer's rule. This a2 is given as the determinant xd minus xu times fd, sorry, this second element, and the second row we have got xuu minus xu, and the fourth element of this determinant is fuu minus fu divided by d. Okay. So next you can expand it, expand the determinants, get the coefficient values a1 and a2, and substitute values of a1 and a2 and of course a0 in interpolation which we had used, that is quadratic interpolation, and then you can find out what is value of Fe, okay, in terms of this Fu plus your A1 times Xe x small e minus Xu plus A2 times x small e minus Xu whole square. Okay. Now, for the further simplification, I would leave as an exercise to you that perform the algebraic manipulations to obtain Fe, or rather the formula for Fe given in the slide. So, this I would leave as a simple exercise which you can work out. So, this is what we had, that if you carry out the algebraic manipulations, you can represent Fe in terms of Fu plus G1 times Fd minus Fu plus G2 times Fu minus Fu, and for your reference the final form for these coefficients G1 and G2 are given here. Okay. Now, this scheme was derived by Leonard in 1979, and he named this scheme as QUIC. The QUIC is basically an acronym which stands for quadratic upwind interpolation for convective kinematics. Convective kinematics, because this particular interpolation would be used for convection dominated problem, and quadratic because we had obtained this interpolation based on quadratic interpolation formula, and upwind is there because we have used the 3 nodes, 1 downstream and 2 upwind nodes. So, that is why the name here is quadratic upwind interpolation for convective kinematics. Now, this particular scheme, it is third order accurate on both uniform and non-uniform grids, and in case if we had uniform grid, we get a very simplified form, that phi at E is 6 by 8 phi at upstream node plus 3 by 8 phi at downstream node minus 1 by 8 the function value at upstream to upstream node. Now, because of third order accuracy, this scheme is again very popular in modeling advection dominated problems. But note here that still there are some issues with oscillations which are fairly similar, they are not as severe as a central difference scheme, but nevertheless there are some possibilities of obtaining unwanted oscillations in numerical solution with use of quadratic upwind interpolation scheme. Now, let us have a very brief look at few other interpolation methods. The first one was what we call hybrid interpolation scheme, which is a blend of CDS and UDS based on the local Peclet number, that is Fe is gamma times FCDS plus 1 minus gamma times FUDS, where this gamma would depend on the local Peclet number. If the local Peclet number is very small, okay, then this gamma can be set to 1, FCDS should be used for the interpolation. If the Peclet number is large, okay, then in that case choose a small value of gamma, so that we make use of upwind difference approximation. So, this hybrid interpolation scheme, it combines the properties of or desirable properties of both CDS and UDS. More recent developments include total variation diminishing scheme, and for details you can see the book by Versteeg and Malala-Sekera. Okay. For instance, here we will express Fe as f at the computational node P plus 1 by 2 psi r Fe minus Fp, where this psi r is a specified function which depends on the local flow conditions. Now, this UDS is one form or like one of these TVD schemes, and formally psi is called a flux limiter function. There are many other interpolation schemes available in literature, and for details please have a look at the book by Chung on computational fluid dynamics, Fertziger and Perik's book, and you can also have a look at the book by Versteeg and Malala-Sekra, which gives pretty detailed introduction to TVD and ENO, that is essentially non-oscillatory schemes. As for this particular course is concerned, this lecture we will stop here, and in the next lecture we will have a look at some applications of the finite volume method to scalar transport problems.